Hi everyone, thank you so much for coming out to the exam review tonight, to the SSC CHEM 1312 exam 4 review. My name is Jeffrey and I am a PLTO leader for Gen Chem 2, and tonight I'll be your host for this review. This review session will be led first with a lecture led by me, and then we'll break out into breakout rooms to handle some practice problems for the upcoming exam. So materials, you can see the QR code, you can scan that for the slides, but they'll be also posted on the Peer Tutoring YouTube channel in the following days. Okay, so without further ado, if you have a question for people joining us live, if you have a question, feel free to put it in the chat, and then one of the support leaders will be there to answer your question. But if there are no further questions, we can go ahead and get started. So we're going to start off with the delta G, talking about delta G, because for exam 3, there was a lot of math, and now unfortunately we're not done yet because we have to relate delta G, what happens when you have non-spontaneous conditions. So last time, for exam 3, you all were given a delta G, and you were asked to calculate that given delta H, temperature, and delta S, which is entropy. However, that can only work whenever you're given the standard state conditions. So what happens when you have non-standard state conditions? So what happens is that we have this initial condition where in this initial formula where delta G naught is equal to minus RT ln K, or you can also find delta G naught from given data as well, just like as you were given in Gen Chem 1 with the enthalpy values, and you also later learn on, you can do that with entropy. However, for non-standard state conditions, the free energy change is delta G is equal to delta G naught. So you have the delta G at naught, which is at standard conditions. And like I mentioned before, you can find this using that formula, the formula, this one, or you can also use the delta H formula, which is delta H minus T delta S. Or you can give there are all the ways you can do this, and you can also find it using the values as well if you're given that. Plus RT ln Q, where Q is the reaction quotient. Notice how K and Q are here. So it kind of makes sense if you're talking about the formula where this is going to be the one standard because we have a K, but this one is non-standard, which is Q. And we know that Q is the reaction quotient at non-standard. And a couple of things to keep in mind here is that there is the R, which is the ideal constant, 8.314 joules per Kelvin. So make sure a couple things here. R is going to be in joules. So sometimes when you're given a problem, you might have in kilojoules. Make sure you always convert to joules. So next, we're going to transition to something a little bit different. If you recall from Gen Chem 1, we talked a lot about redox reactions. And what that essentially is, there are two parts of it. We have an oxidation reaction, and we have a reduction reaction. So oxidation, there are a lot of fun acronyms that you can use. My favorite one is LEOGR. Oxidation is going to be the loss of electrons, so that's loss of electrons for oxidation, and the value becomes more positive. So you do this by finding the oxidation number. If you remember, we have to find first starting the values of, let's say, oxygen, we know it's usually -2, hydrogen, you can kind of like fill in the blanks from there. On the other hand, we have reduction, where it's the gain of electrons. So it would become more negative. So an example would be if something had like an oxidation charge of -2, and then it went to say -3. Oxidation, on the other hand, you become more positive. So that can look like something like +3 to +5. And it can also look something like -2 to 0. Remember that it's also good to keep in mind that your agents are the opposite. So if you have something that's being oxidized, it's going to be your reducing agent and vice versa. So this looks like a lot, but we're going to go through it in depth. So essentially, we talked about last time in Gen Chem 1 where we had to balance out the charges. We do that by multiplying like by the coefficients, cancel out the electrons, and those were in neutral conditions. And what this unit introduces is that what happens when you balance them in acidic or basic condition. So I outlined the steps here for you all. I think this is one of those things where you learn a lot by practice and not by reading. So we'll definitely have a couple of practice problems for you all to work on together, and then to hopefully get the hang of it. So essentially, the first thing you would do is that you would identify your half reactions. This is your oxidation and reduction reactions. And then you will have to balance elements other than O and H. And then in solution, in these acidic and basic conditions, you usually have these ions floating around. You have H+, you have water, and you have electrons. And these are like the basis of what you're going to use to balance them out. First, you're going to balance out the oxygen atoms by adding the appropriate number of water molecules to the opposite side of the equation. So an example of this would be if I have 3 oxygens on the left side, then I would have to add 3 oxygens on the right side to balance out the same amount of oxygens. I think a couple of mistakes that students can make here is that they don't factor in the coefficients. So sometimes when you have, let's say, like a 2 in front of an IO3 minus after you balanced out in step 2 right here, they don't account for that coefficient. Rather, they would say that, oh, it's just 3 oxygens, but rather they have to do 2 times 3. Next, you would balance the hydrogen atoms, including those added in from step 2 to balance out the oxygen atom by adding H+ ions. So make sure you account for that as the coefficients as well. So when you add your O and then H, you balance out everything from here. Now it's time to move on to the charges. So first you would find the net charge by adding up the charges on each side, and you make them equal by adding enough electrons to make them to the more positive side. So here's a rule of thumb: the electrons in H+ are almost always on the same side. And this kind of makes sense because when you're adding electrons, what you're doing is that you're making it more negative, or you're lowering that charge. So you can theoretically make a charge on both sides equal if you just reduce it enough. Next, you would have to combine the reaction, but before you do this, you have to make them the same number. So the electrons on each side must be made equal. If they are not equal, they must be multiplied by the appropriate integers, the lowest common multiple, to be made the same. This can be referred to, or this similarly, we did this in Gen Chem 1, where we identified those half reactions and we balanced them out, both those electrons. But for here, we're just doing a lot of extra steps. Okay, and so the next step is going to be the half reactions are then added together, canceling out the electrons to form one balanced equation. So if reactants and products are on the same side, or on different sides, excuse me, let's say I have water on the left side and then I have water also on the right side from those 2 equations. What you want to do is that you want to subtract from the highest side. So let's say we're going to have the example. Let's say that I have 5 waters on the left side and 6 waters on the right side. You would take 5 waters from the right side, so overall you have 1 water on the right side. So you always subtract from the highest place. And this is for acidic conditions. So different professors teach a basic solution differently. So, but what I find as a student, the most simplest way for me is that we have to add OH at the end to combine the net equation. Some professors will teach it as you're doing it in the middle, but I feel like as a student, that's just really confusing. So what I do is that I teach all my students the same way, where I just add OH minus at the end, and that you'll get the same answer. So if the problem asks for basic conditions, what you want to do is that you want to add OH minus for each H plus on both sides of the reaction. So let's say that after I've done steps 1 through 7, and I have at the end, I have, let's say, 8 H plus on the right side. So if I have 8 H plus on the right side, in basic condition, I'm going to also add 8 OH minus on the right side as well. However, on the basis of that, if I add OH on the right side, I have to do it to the left. Next, you want to do combine H plus and OH minus to make water, and then and sometimes when you have water, you might have a period again on both sides, so you would have to really cancel them out one last time. So if you kind of got lost, that's okay. Basically, a TLDR up on the right, balance your elements other than HO, balance your O with H2O, balance H with H+, balance charge with electrons, and then you combine as needed. And this is one of those topics, like I mentioned, it's easier to understand how to do once you practice, and there are a couple of problems that we'll work on together, so hopefully you feel more confident as you enter in your exam. Let's get started. Okay, so this diagram is a lot, right? But we're going to go step by step. So we have a galvanic cell, and we have oxidation and reduction reactions. We talked about that in Gen Chem 1, but we didn't really talk about like the apparatus that is actually made in. So I'm going to go ahead and just go through this diagram together with you all. So let's go ahead and get started. So usually you'll have like just 2 bins like this separated, And then on one side, on the left side, you have the anode, and then which is where oxidation takes place. And you have on the right side the cathode, which is where reduction takes place. And so I know it's really small here, but on the bottom left corner, what I wrote of the overall like net reaction. So that reads Al plus Ni2 plus yields Al3 plus N2Ni. And if you identify the oxidation and the reduction species, you can see that the Al becomes oxidized, and then the nickel ion becomes reduced. And so that actually kind of is what happens here. So if we start from the left, we have the anode, and that's where oxidation occurs. So the electrode, the anode in this case, is going to be Al, right? And so the Al will be here, and then the electrons will be oxidized. So the electrons, you can see this little drawing here, the electrons go up there. And so that will drop down to Al3+, and that will perform in the solution. And we'll go over, talk about what that solution is. The electrons will then travel. They'll go to this this like little like voltmeter here, and we're going to talk about that too. And they'll go over here, and on the right side, this is going to be this cathode will be made of Ni. That should not be Pt. That should be Ni. So just ignore the Pt, but then this electrode cathode should be Ni, not Pt. I'll go ahead and make that correction, but just be sure that this is Ni. Sometimes you'll have a cathode that's Pt, and we'll talk about the intricacies of that like in next slide. But the important thing is that on the Ni electrode, what's going to happen is that the Ni2 plus will be there, and then the electrons will, the Ni2 plus will take the electrons, as shown here, combine with the Ni2 plus to form Ni, and that will pop off into solution. So that's kind of essentially the apparatus here. So the anode will always be negative, right, because it's where the electrons are starting from, and then they will always go to the positive side. Notice how it goes from a big electron gradient, high to low. The anode will lose mass because it's losing electrons. So naturally, you think that if something is losing something, you would probably lose the mass as well. And the cathode will most of the time gain mass. There are specific scenarios where they don't gain mass sometimes. So we're going to talk about that in a little bit. But we're going to go ahead and talk about this is the E naught. So this is the E naught cell. This is the standard reduction potential. And we talk about E standard cell potential when both of the solutions are 1 molar. This is really important. What happens when it's not 1 molar? We'll talk about that as well later on. So essentially, the formula is E anode plus E cathode. In some textbooks, you'll say that it's E cathode minus the E anode. And so essentially, both mean the same thing, but there's a few key differences. So in this formula that I've written here, that's the one I kind of go by, because the E anode and the E cathode, these are values from the reduction table. But the thing is, from the standard reduction table that you know from Gen Chem 1, that all of that has the reducing potentials, right? So all those reactions, they're reduced. And in this apparatus, the galvanic cell, not everything is reduced. Rather, we have one reaction that's going to be oxidized and one reaction is going to be reduced. So to account for that, we need to flip one value. And so the goal of the E naught cell value is that you have to flip the value that will yield the highest E cell. Let's say that I have one potential that's, let's say, 1.34 and another one that's negative 0.31 example. So that negative 0.31, I want to flip that because I want to get the highest E cell value. This is when the reaction will be spontaneous. Now, when I flip that negative 34, that is going to be my E anode. So we'll go into detail more of this, but essentially the formula would be negative of the negative, so negative of negative 0.34, since I flipped the reaction to make it oxidized, and then plus the E cathode as well. That is a lot, so if you have any questions, feel free to ask in the chat, but we're going to go over that in practice problems too. So a couple things here that I would notice that. So notice how naturally electrons go from the left side to the right side, and so you would think that that there would be an accumulation of negative charge here on the right side. So this would kind of render the galvanic cell useless, because the only reason why those electrons move is that it goes from a high gradient to low gradient. If you remember from like a bio class in high school, or if you're taking one right now, that's the things how it usually moves because of diffusion. So like high concentration of electrons move to low concentration of electrons. And so naturally, that high accumulation of electron that will kind of render this gradient useless, because, you know, eventually there would be a point in time where on the right side there would be more negatives than the left, and so it kind of fluctuates the system. To prevent this, this solution is made up of a salt bridge. And so what the salt bridge is that it allows for the migration of charge so that K minus can flow. It will usually be made of inert compounds like KNO3. And so if more negative charges are coming here, you want the cations from the salt bridge to balance out that negative charge. And intuitively that makes sense, because to counteract that accumulation of negative charge, you will want the positive cations to go to the right. On the opposite side, a generation of Al3 plus here is going to be really positive. We don't want that to disrupt the gradient as well. So what we're going to do is we're going to put the salt bridge in, and so the NO3 minus therefore is going to move to the left, like I've written down here, and so balance that charge. This is going to be this is only for 1 molar solution, and so you'll have like usually you have 1 mole that says Al like SO4, right? And so usually have like solution here, so that those elements recombine, and these cations recombine, and then they prevent that charge from from accumulating as well. Another way you can represent this apparatus is by this notation here. So the first one is usually made of what the anode is. So in this case, the anode is Al, right? And then on the right, on the next part with the Al plus 3, 1 molar, it's going to be what the solution is made of. So that's going to be Al plus 3, because that's the cation in solution. On the right side is going to be the cation or the ion in solution on the cathode side, which is Ni2 plus. And then it's going to be on the right side right here is going to be the Ni. One tip I can give you is that if you break up these half reactions, Al is going to be like notice how Al is right here, and then Al is right here. So the left side of the reaction will be on this part of the oxidation, and then on the right side, that ion will be right here. Same goes for here. Ni2 plus, that ion will go here, and then whatever's on the right, whatever's on the right will be that cathode, if you can see that relationship. This cathode sometimes is very finicky, because the only time this is made is going to be the same is when on the right side of the reduction reaction, it's not a ion. And why though? And we're going to take a look at here. Okay, so sometimes the cathode will not gain mass at all, since even though we talked about that, if the cathode is not made up of the reduced product. So in this case, the cathode cannot. So let's take a look at this reaction, right? This over here on the left is going to be Cu to Cu2 plus 2 electron minus. And on the right side, that's very small, but Cr2O72 minus is going to be produced to make 2Cr3 plus. So if you think about it, on this side, notice how on the right side of the reduction reaction, it's you would think that, oh, that's what the cathode's going to be made out of. But in this case, the right side of here of this reduction reaction is the Cr ion. And so these cathodes, these electrodes cannot be made out of ions. Why? Well, because if it's an ion, if this cathode was made up of an ion, what's going to happen is that ions readily form ionic compounds in solution. So if I randomly put like this NO3 minus here, that Cr is going to make Cr like NO3, and that will disrupt the mechanism for which this works. So therefore, that cathode has to be made of an inert metal. Sometimes you say PT, sometimes gold, but it has to be inert. So in this case, if you're generating an accumulation of Cr3 plus, if a question were to ask what happens to the charge of what happens to the mass of the cathode, well, nothing happens, because Cr3 plus is generated, and notice how PT isn't made in this reduction reaction. It's gonna not change the mass. That was a lot to say. A question is, a Cr3 plus is already present in solution. That is a good question. I would say that it's generated as the reaction is moving along. So Cr2O7 minus, I would say, is like kind of already there, but then as the reaction is generating, the Cr3 plus is generated. It's a good question. Okay. Thank you for the question. If you have any more, please type in the chat, and I'll be more than happy to answer them. Okay, so let's expand on that ESO math I was talking about earlier. The ESO math with standard reduction values, you have to do 1 molar for this. Both sides have to be 1 molar. I can't stress that enough. So it's ESO is equal to E cathode plus E anode. Make sure you flip the E anode. The goal is the highest cell ESO value. you must flip the E electrode potential value to make the overall E cell value large as you can. When you do this, you have to flip the corresponding half reaction too. When you flip the reaction, it turns, instead of being written as a reduced reaction, it's going to be written as an oxidizing reaction instead. The reaction you flip becomes the oxidation reaction, which is at the anode. The question is, so the reason why we can't have PT electrode is because this electrode can't be made from chromium 3+. Yes, that is correct. With the E cell, you can also relate to E cell delta G naught K. So we learned from exam 3 that delta G naught is equal to, we know that exam 3 is negative, from exam 3 that delta G naught is minus RT ln K. So you can use algebra to solve for K. Another formula that's helpful is delta G naught is equal to negative NFE, where N is the number of electrons involved. F is equal to 96485 coulombs over a mole of electrons. And we make sure to balance out the half reactions for N. Okay, so with that being said, let's go ahead and move on to the next question. The next slide. So this is the inertia equation. Combining the following equation from last exam, we have this, or that's the one we talked about earlier. The biggest thing I want you all to know is that the ones in highlighted, so E cell is equal to E cell naught, which is the one at standard values, minus RT NF ln Q. There's also another formula for log. I think it's 0.059 something over N ln log of Q, but I think it's written here. Yeah. So this value, the E cell on the left side, is going to be your non-standard value, and on this one, E cell naught. Don't get those confused. That's going to be at standard conditions. How do you find this? Well, you find it using the reduction values with the voltage on the back. So like the long list of tables, you first calculate that from here, using the principles that we talked about here, and then you can use this formula minus RT NF ln Q. Because of at standard conditions at 25 degrees temperature, this is equal to that, so you can simplify it down to this value. So this is only when you have it at 25 degrees Celsius, but if it's not at 25 degrees Celsius, you have to use this formula. Notice how these numbers change. I recommend picking one and saying with the other. Picking one and saying with that one. I personally use this one, the log of 10, but if you want to use natural log, don't get the numbers mixed up. So that was what a galvanic cell was. Now let's talk about electrolytic cells. So we can use chemical energy to do work instead of electrical energy. So therefore, you're gonna use a non-spontaneous reaction. In this case, you have like a battery. You actually need to take energy from that, and so to really have this reaction occur. The constants. This is the Faraday constant. It relates 96485 coulombs for 1 mole of electrons, where R is 8.314 joules over mole times K. Formulas, another formulas. Voltage is, you can essentially take, like just for Gen Chem terms, it's essentially the amount of like power something has. That's my best definition of it. I'm not a physics teacher, but it's going to be joules over coulombs. So this is current, however, is going to be A is equal to C over seconds. So using these relationships, you can kind of do dimensional analysis, and we're going to do some practice problems on that. Okay, so here are the differences between the electrochemical cell, the galvanic cell, and the electrolytic cell. I'm not gonna go over and read this for y'all, but basically the gist is that this one turns chemical energy to electrical to chemical for this one. Another big thing to point out is that this is going to be the spontaneous part, and this is going to be the non-spontaneous reaction. This is denoted with usually a positive E cell value. This is going to be usually a negative one. And here's like kind of a apparatus for you all to refer to. And then these are, you notice how G is going to be less than 0, which is spontaneous, and G is going to be greater than 0. Notice how there's a battery here actually supplying this this mechanism. Okay, so that was pretty much it in terms of the lecture. We're gonna go ahead and take a quick 5-minute break. So maybe around 7:33, we'll go back and talk about practice. We'll break into practice rooms and really work on some practice problems together. So feel free to go and take a quick break. Okay, everyone. Welcome back. We're gonna go ahead and tackle these practice problems. So, I'll give you all a little bit of time to work on. Give you all a little bit of time to take a read of this question, and we can take a look at it together. Okay. So this problem is after calculating delta G, find the value of K and explain how the signs of both values relate to each other. So let's go ahead and take a look at this, right? So we have delta G at non-standard conditions. So the formula for that would be delta G is equal to the delta G naught, right? Plus RT ln of Q. So to make things easier for you all, I would recommend solving for the individual parts. And what I mean is first I would find Q, and Q is going to be products over reactants. So 0.021, because that's our 0.21. And so that's going to be our NH3 concentration, and then that's going to be taken to the power of 2, because don't forget the coefficients, over 2 times 7 to the third power, which is going to be those values respectively. So on your doing your exam, be sure you match the correct one, because you don't want to do like the math right, but then mix up the wrong concentrations. That's going to be 6.4 times 10 to the power of -7. So notice how we can just go ahead and start filling out. This is going to be 8.314 joules per mole times Kelvin, and then that's going to be times 100 plus 273. And then ln of 6.4 times 10 to the power of -7. So what do we put in for G naught? G naught is given here, but notice how this is in kilojoules, but the R is going to be in joules per mole per Kelvin, and so we have to multiply that by 3. So we can just say times 1000, or 10 to the power of 3. So we can go ahead and put that times 10 to the power of 3 joules, and I'll let you practice and put in that into your number, your calculator. And if you all have any questions, feel free to let me know. Yes, that's correct, Maria. For Q, we only count gases. So if there's something that has like an S in it, if a solid, a liquid, you don't do that. You only do it for aqueous and gases. Okay, so if we do that, this is the number that I got on my calculator. 3 kilojoules, and that's one part of the problem answered. Next, it asks us to find the K value. So we have a formula relating to that is delta G naught is equal to minus RT ln K. Notice how this is different from delta G, where delta G is going to be the one at non-standard conditions, and the G naught will be non-standard. Delta G regularly is going to be non-standard, while delta G naught is going to be standard. So plugging the numbers in, delta G naught we know from the problem is this value equal to minus 8.314 times 373 ln of K. And so once we solve for K, yeah, that's perfect. Yeah, then that's the same as the written. That negative 76.93 kilojoules per mole is going to be the same number as I wrote up here, but I just put it in scientific notation. So what was the minus NFE equation for? I believe that is going to be for delta G. Delta G naught, I believe. Let me double check. Yeah, delta G naught. So if you have delta G naught here, I think that's a really good question, because the question is, what was negative NFE equation for? So in this problem, delta G G naught was given. So if delta G naught was not given to you, you would have to do minus NFE. But that's only for like in the electrolytic cell, but we're not given electrolytic data here. So in this case, since we're not given electrochemical data, delta G G naught is given for us. I hope that answers your question. And if it doesn't, let me know. Moving on though, once we have K, we're solving for K. If we isolate the variables, we get this over from here, from algebra, and that's going to be a really big number. So if you plug into this calculator and you try to get a numerical value, yeah, so the delta G we used was minus RT ln K, because in this case, we're not dealing with electrolytic cells. We're just dealing with just the gaseous concentration. So that's why we do minus RT ln K instead of minus NFE. Those are good conclusions to draw. Yeah, good question. So if you notice, if you plug into this calculator, your calculator, you get an error message, and that makes sense because remember that K is greater than 1. It's going to be the forward reaction. And that kind of makes sense because K is so bigger than, so the reaction would be spontaneous because delta G is negative. Yes, that is correct. And that brings to my second point. We see that in this problem, K is like super big, so K is greater than 1, the forward reaction here. But if we also see our delta G, which is up here, we also conclude that delta G is very less than 0. And so both of these will indicate that the forward reaction, here I'll write this in a different color. So both of these indicate that, so both of these indicate that, so this here and this here, the forward reaction is preferred, and thus is spontaneous. And remember, when we learn about delta G, if it's spontaneous, is going to be like super negative, and we see that here. So that can conclude that. So these values make sense. Values in terms of their numerical values make sense. On the converse side, if you have a small k, like k is less than 1, you expect your delta G to be like super positive, and overall everything would be non-spontaneous. So that's a good question. That's a good point that someone mentioned. So the reaction would be spontaneous because delta G is negative. Yes, that is correct. Cool. What is the difference between the delta G we solve for and the one given? That's a good question. So anytime you see a knot right here, and this is going to be at standard conditions. So standard conditions at 25 degrees Celsius, 1 molar, right? But then the regular one without the knot, it's going to be at non-standard. So this was at something other than room temperature, which is like, right here. That's not 25 degrees. So so delta G naught, anything in chemistry, you have a naught, is going to be under the one. Oh, you meant the one under the RT ln K. This one? Oh, okay. So this one, yeah. So this one, are you talking about this one? So this one is going to be just the delta G naught at standard. Yeah. So this one is going to be at standard conditions. So standard condition, and this one is non-standard. Non-standard. So this one you do when you have the standard condition, it's 25 degrees Celsius, yada yada, and then you have this one which is not at standard. So a temperature different at 25 degrees Celsius, which is like, and that shows right there. And you can kind of tell too, because K is used for equilibrium, so standard, and then Q is like not standard reaction quotient. Yeah, good questions. Does anyone have any other questions? Okay, yeah, no worries, good question. Okay, so let's move on to the next one. So this one, these problems are kind of long, so if you all have any questions or want me to stop anywhere, just let me know. But we're given balance equations of the following conditions. So the first step I would do is try to identify your half reactions. So here's a little like review for oxidation states. So to find the oxidation number, you first have to start with the number that you know. So for instance, we know that since oxygen is in the group 6, it's naturally going to form a -2 charge, because to fulfill the octet rule, you're going to have to gain 2 electrons. So naturally -2. Going from here, overall, those 3 oxygens will make a -6 charge to the molecule because there are 3 of them, each -2, so it makes sense. And then this has to equal to -2. because the charge for this polyatomic ion is -2. We don't know what the S is, so we're going to call that X. Solving for X, since there's only one of them, we can just put a 1 in front of it, and that's going to give you +4. So that's +4. Next one, if we follow the same principles, we get -2 for the O here. Then x minus 8 is equal to -1. That's going to be your x for Mn, -1 for the overall negative charge, -8 because they're all of them. So that's going to be +7. So this is +7. So next we have the other ones, trying to do that here. So -2. So -2 overall is -8 equals to -2. We have 1 SO4. So x is equal to +6 for here. That's +6. And then +2, and then 2 plus by itself, we can just say that's +2. Because it has a +2 charge and it's by itself. Okay, does anyone have any questions on this? Okay, if not, if you do, just let me know. I don't mind going over it again. So next we have to identify what's oxidation and what's reduction, right? So if you remember, oxidation is you gain more positive charge, and I see that the S goes from +4 to +6. So we can say that our oxidation reaction in this case is going to be SO3 2 minus, and becomes oxidized when it turns to SO4 2 minus. Reduction reaction is going to be, I notice that the Mn goes from +7 to +2. It's decreasing in charge, so it must have gained an electron. And that's going to be MnO4 minus to Mn2 plus. Okay, so if you have the PDF of the slides, you know that first we got to balance out the oxygens. So notice how I have SO3, 3 of them here, and SO4 of them there. So to balance out the oxygens, we have to put an extra H2O plus SO3 2 minus to SO4 2 minus. Okay. Does anyone have any questions? So it's really important that you ask questions if you're lost in a step, because if you're lost in one, then like it kind of tumbles down. So if you have any questions, do let me know. But if not, next, since we added the SO3, we added the H2O, we kind of have to fill out the the hydrogens. So we have 2 hydrogens in here, therefore we have to add 2 hydrogens on the right. So I'll show that with a different color, and we'll do that in green. So that's going to be blue, sorry. That's 2H plus. Okay, does that make sense for everyone? Okay, so next we have to count the charges. So we have, so I'll do that in a different color too. So we'll do that in, I guess, red. So this one has a charge of 0 overall. Overall, this one has a charge of -2. This one has a charge of -2, and this one has a charge of +2, right? So overall, the net charge for this left side is -2. Overall, from the right side is going to be 0. So we need to make them equal. So to do this, since you want the right side to gain a -2 charge, all you have to do is just add 2 electrons here. Okay, and we are done. I'm going to highlight this because this is our end product that we will be using later on. So highlight that one. Okay, now we got to do it we got to repeat this step for the right side. So I'll give you all a second to do that, but if you always want to try, but we're just going to go ahead and move on. So I noticed that I have 4 O's on the left side and 0 O's on the right side. So I need to add I need to add 4 hydrogens here. 4 H2Os, excuse me. So once I do this, right, the O's are balanced, but now I need to really take a look at the hydrogens. So I'll do this in this color blue like I did with the previous one. And notice how there's going to be 8 on the right. Now I need to put 8 on the left too. So once I do that, the charges are imbalanced. But how are they imbalanced? Let's take a look. We have a net charge of 8 right? 8 from there, 8 from the 8H plus, and then we have 8H plus 8, and then we have a minus 1 here, so that's going to be overall plus 7, and then we have plus 2 here. So to make them the same charge, we can add 5 electrons on the left side, so 5E minus plus 8H plus MnO4 minus 2 Mn2 plus 4H2O. And if you ever want to check your work, you can do it midway too. Make sure first you like, oh, I'm going to check on the left side. Do I have 4 oxygens? Yes, I do. On the right, yes, I do. On the left, I have 8 hydrogens. Do I have it here? 8H, and there's 8H on the right side. Next, I want to balance out the charge. So if you count, overall you'll have like 5 minus 5 plus 8 minus 1. That should give you, I believe, plus 2. And then the right side is plus 2 as well. So we need to combine both of these, right? So I'm going to go ahead and tidy up my work. So H2O plus SO3 2 minus yields this. And we got that from that reaction up there. And then there's another one, which we just got. Okay, so next we got to combine them. But before we do that, we need to first make them have equal coefficients. So for the electrons. So this is 2 electrons here, and this is 5 electrons here. We multiply next. We multiply everything. We have to multiply this by 5, everything up here. So this becomes a 5, and this becomes a 5, and this becomes a 5. This becomes a 10. And then at the bottom, we multiply everything by 2 because to get the same electrons. So this becomes 10 electrons. This becomes 16. This becomes 2. This becomes 2, and this becomes 8. Okay, so I'll give y'all a second for y'all to try combining these two. And then we can talk about the final product. Okay, so let's go ahead and work through this together. So I always like to start with the electrons and then the H and then the water. So notice how these electrons, there's 10 here, and then there's also 10 here, so that cancels out. If you did this correctly, you should have electrons to be canceled out. And then move on to the H's. So I have 16 on the left right here, and then I have 10 on the right. If we subtract from the side of the bigger, 16 minus 10 is going to be 6H plus. And then let's move on to water. So water on the left side has 5 of them, and then on the right side, there's going to have 8 of them right here. So overall 8 minus 3 on the right side is going to be 3H2O. And then we can combine the other elements that we didn't use. So I see that I have a SO3 2 minus, which is from here. I can drop that down on the left side. And then I also have a 2MnO4 minus from here. On the right side, I have 5SO4 2 minus, which is right here. And then I have the 2Mn2 plus, which is right there on the right side. So this is a lot. I recommend just downloading this PDF of this worksheet, and then kind of see if you can rework this problem. See if you can get the correct answer. So does anyone have any questions? I know that was a lot. Okay, if not, then we can go ahead and get started with the next problem. So let's first identify the half reactions here. So, but before we do that, we gotta list the oxidation numbers. Ag by itself is 0. Zn is plus 2 if it's charged by itself. We know that oxygen is usually minus 2, and then to balance out the minus 2 to give it a 0 charge overall, you need to have the Ag to be plus 1, because 2 pluses 1 make a negative 2, so this is plus 1. Zn by itself, we know that's 0. So oxidation, I see that my Ag went from 0 to plus 1, and I can say that the oxidation half reaction is Ag to Ag2O. My reduction, on the other hand, reaction is going to be, I noticed that Zn2 plus, Zn went from Zn2 plus, and then it went from to Zn, and so that's going to be my reduction reaction. Okay, so first balancing out, we need to make sure that every element besides H and O are balanced. So this is going to be 2, right? So on the left side, there's going to be 1, but on the right side, there's 2. You got to put a 2 in front of this, so 2Ag yields 2Ag2O. And then what's going to happen is we're going to have another one where, notice how we have 2 times 1 oxygen right on the right. So we got to add 2Ag plus 2H2O on the left. And then we have this over. However, once we do that, I notice that there are 4H plus on the 4H on the left, and then I need to put 4H plus on the right. So 2Ag plus 2H2O yields 2Ag2O plus O plus 4H plus. So if I look at the charge on both sides, which is what we're going to move on to, I notice that this one is going to be a 0 charge, and this one is going to be a this one is going to be a 4 charge. Wait, I'm sorry. Let me go ahead and quickly just double check my work. So G2 and then yeah, you are correct. I accidentally put an extra 2. You are correct. Thank you. I was looking to see where I made a mistake. That is correct. Thank you so much for catching it. So you do that, and we just need one of them. I don't know why I put a 2 there, but we just need one here, and then we need one there. Excuse me. Sorry, you all. So fixing our work, we can have one H2O, and then we have this 2Ag plus H2O yields Ag2O. So for fixing that, we just need 2H plus. So let me go ahead and just tidy up that work for you all. Then selecting the pen, 2Ag2, 2Ag2O plus 2H plus, right? And so we only need 2 here because on the left side we have 0 charge, and then we have this is going to be plus 2, right? So E minus. So one of them would be an E minus to balance out. So it would be 2Ag2O plus 2E minus plus 2H plus. Even in basic solutions, do we add only H2O and H plus? Do we ever OH minus? So that's a good question. So in acidic or basic conditions, you always add H2O and H plus. However, you do have to add OH minus too, but the way I teach basic condition is that I add the OH at the end so that we don't get confused. That's a good question though. So repeating that again, basic condition, you do add H, yeah, okay. Oh, okay, we got it, that's good. And I'll let you all think about what we're gonna do next on the right side, and I'll get back to you and we can move on. Should the final solution have only one Ag2O? Yes. I forgot to clear that typo. Thank you again for reminding me. You guys are experts at this. Already correcting my work. I appreciate you all. You guys are gonna do great. Okay, so just erase that. Yeah, good catch. Thank you. Okay. So I'm just gonna tidy this up for you all because a little bit of confusion. So the overall reaction would be Ag2O plus 2H plus E minus. Okay. Now on the right side, we have a Zn2 plus and then Zn just regular. So we don't need to balance out the H or the O. We just need to balance out the charges. This one has a plus 2. This one has a 0. To make the balances the same, we can add electrons to the left side, and it's just easy as that. Sometimes they'll be easy like this, sometimes they won't. So it really depends on the exam. Okay, so combining these equations, right? Okay, so that scribble. So we have 2 Ag plus H2O yields Ag2O plus 2H plus 2E minus And then from that, the one we just did, Zn2 plus 2e minus 2Zn. So in this case, we don't have to multiply by the common common multiple because they're already done with us. So cross that out. And so let's go ahead and combine them together. So I noticed that always do the H plus first and then the water as well. So I noticed that on the for water, there's only one on the left. And then on the right side, there's only 2 H plus because it's from this one. And then we take a look at the other ones. So there's going to be 2 Ag and also 2 and just a Zn2 plus. And then we also have a 2H plus. We also have an Ag2O. Okay, but we are in basic condition, right? So something that you would kind of forget to do in the exam and cost you points is that you don't do the hydroxidation. So I say that do this at the end. If you do it in between steps, like if you add hydroxides, like this step right here, when we balance that, that's fine too. I just feel like as a student, that's just really confusing. So I rather wait to do it at the end. And either way will give you the same answer. So we add 2 OH minus here, and then we also add 2 OH minus here, because we got to do one side, you have to do to the left. So this combines to 2H2O. Overall, our balance equation so far is 2OH minus plus 1H2O plus 2Ag plus Zn2 plus. I'm just gonna go ahead and write it on this right side, y'all, so there's just no space. So that's gonna be, as I mentioned, 2OH minus plus 1H2O plus 2Ag plus Zn2 plus yields Ag2O plus 2H2O. And then we gotta do 2H2O. Right? Anyone have any questions on that? And that's very squiggly, but so next we got to combine our waters. So we notice how there's a 1 water on the left side and then 2 on the right. So just subtract this one and then make this a 1, and then this is your final answer. That is 2OH minus yield plus 2Ag plus 1Zn2 plus yields Ag2O and then 1H2O. Okay, that was a bit of a doozy, but just get some really good practice for this one. And yeah, does anyone have any questions? Okay, if not, let's go. What about the Zn? Oh, that's a good catch. Okay, and the Zn is also beyond there. That's a good catch. Yeah, thank you. I'll go ahead and make that in my notes as well. Okay, that being said, let's move on to the next problem. For questions 2 and 3, refer given the standard cell potential at the following 25 degrees Celsius, so we're at standard conditions. We have that notation. So A asks us for what are the half reactions taking place in the cell? What is the overall reaction? So if we look at this, right, we know that this is the anode, right? And if you read it, Pb will be oxidized to Pb2 plus. So for oxidation, that's going to be Pb for Pb2 plus 2e minus. And then at the cathode, we're going to have Cu2 plus. It's going to be reduced. It's going to take those 2 electrons and yield it to Cu. So we can cross this out and then balance it out. If it wasn't crossed out for you, if they weren't equal, if they weren't balanced already, if they had different electrons, you would have to multiply. If anyone of you were wondering, Pb2 plus and then Cu, and this is the overall reaction. Okay, so next is calculate E cell knots because we're doing a standard condition, delta G naught, and then K for this equation. So let's start with E cell, right? We know that's equal to E anode plus the E cathode So we know that the reduced one, the cathode, is going to be this formula, is this one right here. So we can say that's 0.34. Do we have anything that looks like the PB to PB2 plus? So PB, we have something that looks like this. We have something that looks like it, right? We have this one, but notice how this, the reactants and products, they're flipped. So we got to flip it then. So E cell would be negative of the negative 0.13. What if there are different amounts of electron? Do we multiply so we have the same amount of electron? Then answer for the reaction of an electrode? Yes, that is correct. So, and if we're referring to A, 2 electrons are involved, right? But if this was like, if this ox was a 3 and this one was a 2, you have to multiply by the least common multiple, and so therefore you would get 6 electrons involved. That's a good question. Does that answer your question? So if there was a different amount of electron, we have to multiply the same amount of electron, then answer for the reaction. Yeah, for sure. Good one. If you have any other questions, just do let me know. Okay, so, but continuing our math, we get 0.47 V voltage. So that's E naught cell. Okay, now we're asking to find delta G. Okay, so delta G naught, we know. Now this time we have to use the formula that relates E cell to delta G. So is equal to NFE E. Okay, so this is the electron involved for N. This is the Faraday constant, which is that value. And then this is going to be the E we calculated, so 0.47. So if I multiply this into my calculator, I get 90695.9 joules. How do I know this is in joules? If you're wondering, because the Faraday constant is in joules. Okay, so feel free to number the calculator. Sometimes I do make errors, but if you want to double check, feel free to do that. But moving on, so is it negative? Well, let's see. So yes, it is negative. That is a good catch. Thank you. So we have delta G naught, and we're asked to find K. So delta G naught, the formula relates that to K is 9 RT ln K, and we know this from exam 3. That's how everything doesn't go away. So plugging in our numbers, we have this value is equal to minus 8.314. Temperature would be 25 plus 273 over ln of K. And so simplifying that, you get E of let's see. E, I did not mean to open that menu, so you get E to the power of 36.60. Okay, so let's kind of look at the values here, right? So we have a high value of K, right? A really big positive one. So we know that it's the forward reaction is going to be preferred, right? So if a delta G, if we know that the forward reaction is preferred, it can be also say that it's spontaneous. And spontaneous delta G values are negative, really big negative values, which we see here. And negative delta G naught values correspond with positive E cell values. So, and that's what we get here. So, conceptually, it makes sense, all these three. Okay, so let me know if you'll have any questions on that. Okay, cool. Let's continue on. Okay, so we have this number, right? We have which electrode is losing mass and which electrode is gaining mass. So the anode loses mass, so PB is lost, and then cathode is gain mass, and that's Cu. So a common trick is that we need to check if the cathode is made above of a what's it called, of the same kind. So if this was something like PT, like this guy here, we wouldn't say that it increased mass, but because for this product, the end product is going to be a solid, right, in the ion, so it can be the cathode. If you look at this problem, for example, like this one right here, if you had Cu2+, if this was in the cathode, you have to use an inert metal, which I was talking about earlier, because this one cannot be the electrode, or that cathode specifically. Okay. Next is D, right? So draw the galvanic cell for this reaction, show the electrodes, whatnot. So we got to do this one, two things, right? So we have the anode here. The anode is made up of Pb. What's in solution is going to be Pb2+. It will give the electrons here to power that up. And then on this cathode, we would have the Cu2+, right? On this one, and then that will be turned to Cu. Like that. Okay. So this one, what's it called? The anions will move here, and then this one would be the cations to balance out those charges. Okay. If those concentrations are present, what is E cell? Relate this answer to Le Chatelier's. Okay, so we have this one. It's not 1 molar each, so we're going to use that equation. Assuming this is at the same temperature, right? At 25 degrees Celsius, you can assume that E cell not is going to be E cell naught minus. I like to use the log one. You can use the ln one. It's fine. Log of Q. Now, if this wasn't at 25 degrees Celsius, if it was like 100 degrees Celsius, for example, you would have to use that expanded one with the NF at the bottom from the PowerPoint. So moving on, we get E cell, which is recalculated, which is 0.47 over 0.05916 V over n electrons 2. And then we do log of Q, so products are reactants. So Pb2 plus for quintuple equation is going to be the product, and Cu2 plus is the reactant. Therefore, we can say that plugging in is here is going to be 0.25 over 0.13. And doing this math will give you 0.4616. Okay, so let's think about it here, right? So in this case, we have more products, right, than more reactants. So if you remember, for some reason, I can't see your annotations. Oh, I'm sorry to hear that. Maybe if you refresh the page, it should be appear, but is it appear for everyone? Is anyone else having difficulties, or can you all see the notes that I'm making? Okay, yeah. So I would try refreshing your page if you can. Okay, so we have more products and more reactants, right? So if you remember from the how K works, or Q, when this happens, you go in the reverse reaction, right? And so reverse reactions, and that's how to think about how we do that for an E cell value. So E cell, when it's greater, is like bigger than 0. It's going to go from left to right, right? So we would think that a smaller E cell value. Okay, no worries. If you have to go, then the practice problems will be posted, so you can review them later. But yeah, thank you for showing up. Good luck. So on the other hand, if you go from if the E cell value is still greater than 0, but it's not that big, it goes from right to left. So let's take a look at here, right? This is the calculated one. Right? This is the one we calculated at non-standard. And this is the one that we calculated at standard. So 0.4616 is less than 0.47, and that kind of makes sense because since the products are preferred, you would want to you would predict that the E cell would decrease because you're approaching the cell where it has more product than reactant, so the E cell would shrink because we don't want this reaction to go now since more products are reactants than reactants are present. Okay, so let me know if y'all have any questions or want me to repeat that. Let's take a look at 3. So I'll leave you all to read that problem, and we can work on it a little bit. Yeah, so in this case, the E cell is less because notice if you look at the concentrations, there's more product than reactant. And so because there's more product than reactant, we know from K that the reverse reaction would occur. And so when the reverse reaction occurs, this goes from right to left. And so E cell values, a smaller E cell value means that the reaction is not proceeding in the forward reaction. So it goes from right to left. And therefore, it kind of makes sense to see why this E cell is less than the one up here. So essentially, it's because there's more products than reactants, so the reaction kind of stops going, which makes a smaller E cell value. If on the other hand, there would be more reactants, then the E cell value would be greater. If there were more reactants than products, then the E cell value would be greater than predicted. Okay, so let's move on to the next problem. So the next problem says that for question 3, use the table of reduction potentials to create a cell in which you get the most spontaneous oxidation and reduction in the galvanic cell. So this is the table, right? So we want the highest one, right? So if we want the highest one, we would take the highest value here, the highest negative value, and then the highest just normal value. And we're going to see why. So if I write this out, we get Zn2 plus 2e minus Zn. That's going to be volts. And then this is going to be Cu2 plus 2e minus. That's going to be Cu. So that's going to be 0.34 volts. So we can't have both negatives, right? We got to flip one. And we got to flip one to make a negative one, to make something that's going to be bigger. So this one is going to be, if we flip this one, if we do Zn to Zn2 plus 2e minus, that turns into this, and then this will be plus 0.76, okay? We have E cathode plus E anode is equal to E naught cell, and so the E cathode would be the 0.34 because we're not doing anything to it, and the E anode would be the one that we're flipping, which is 0.76, and then that's 1.1 voltage, and that's going to be E cell. E naught cell. So E naught cell. So this is going to be E naught cell is 1.1 voltage, and the overall formula, if you were to ask, it's Zn plus Cu2 plus to Cu plus Zn2 plus. How do we get this? We just combined this formula, this one, and then this one, and just cancel out. Notice how we didn't have to do anything to the electrons because both of them have 2 on both sides. Okay. I'm not going to do this one because it's just a rehash of like the other problem up here, the drawing. Just know that the oxidation goes on the anode, and then the right is going to, and then the reduction reaction is going to be the cathode. So let's talk about the next problem. What is E cell when the concentration of the ion is the cathode is that value? So E cell, right? So this is non-standard, so we got to use that big equation. So E cell minus 0.05916 of n log of Q. Like I mentioned earlier, if it says that it's 100 degrees Celsius, you gotta use the NF formula at the bottom. I mean, accounting for the temperature. Okay, so E cell is 1.1, which we found up there, and then this is that value, and then 2 electrons that's involved, and then we have log of products or reactants. So the cathode is going to be always the product, and the reactant is going to be 0.230, and that's going to be, doing the math, you get 1.09. And this holds true because more concentration of product than reactant, you would expect the E cell to go down. Okay, awesome. Anyone have any questions on this? Okay, so it's just 2 more problems to go. So how long must a current of 5.7 amps be applied to a solution of SN2 plus to produce? 32.5 grams of SN metal. So we're going to do some dimensional analysis here. Why did we use the log equation for 1e? I thought it wasn't standard. So you use the log equation because it wasn't standard. Yes, that's correct. So you use this equation. So we use, let's do that in. So you use this equation when it's non-standard, but you do this one when this is standard. So like I was mentioning, I thought you can only use it when it's 25 degrees Celsius. Yes. So this is inferred. It's assumed that this is at 25 degrees Celsius because it didn't say so. But if it said, you have to do like the really longer one with the RT over NF. If you look at the PowerPoint, if it says that it was 100 degrees Celsius, then you would do that formula. I hope that answers your question. If it doesn't, then let me know. Oh, okay. Yeah, so that's a degree Celsius. Sorry. Yeah, no worries. I think I was a bit lazy doing the exponent sign, so I just left it as is. But yeah. Yeah, good question. Thank you for clarifying. Okay, so going into this problem, first, one relationship I can find is that SN2 plus produces 2e minus, uses 2e minus to go to Sn solid. So let's do some dimensional analysis. So we given off of this, right? So how long must the current be? We gotta do some formula. So we gotta relate A is equal to coulombs per second. So it makes sense that if we're looking for long, seconds is equal to coulombs over amps. So this equation is from the PowerPoint. So we have 32.5 grams of SN metal, right? First we can turn that into moles. So 1 mole of SN is equal to this amount of SN grams. And then once we get that, we do have moles of SN. According to this up here on the top right, that equation, 1 mole of SN yields 2 moles of electrons. And we can relate that. So 1 mole of SN relates to 2 mole of electrons, right? Okay, and so we know from Faraday's constant that 1 mole of electrons is equal to 96487 or something like that coulombs, and that's going to be equal to 52831.7 coulombs. Okay, so we have that part. We have this part. The amps that we're given, which is like right here. So to find the answer, all you got to do is plug in this number over this number. This yields 9268 seconds, which is your answer. Okay, so this is just one big glorified dimensional analysis problem. Okay. Does anyone have any questions for this one? Okay, if not, then we can go ahead and get started on the next one. A faucet is plated with 0.98 grams of CuSO4 and electrolytic bath at 13.4 minutes or for plating. What current is needed? Okay. So we are talking about current, which is like an ampere, right? So this is A equal to C over S. So we are given seconds, right? So we do 13.4 times 60. I know that that's going to be approximately 804 seconds. So we have this one, right? Now we just need to find coulombs. We kind of work the train tracks again, or like the dimension analysis. So 0.98 grams of Cu. I know that 63.546 grams of this turns into 1 mole of Cu. And then this is going to be 1 mole of Cu yields 2 moles of electrons. How do I know that? Well, I know that this is Cu2 plus, right? Because SO4 is 2 minus, so to balance out the charge, Cu must be 2 plus. So that's going to be Cu plus 2. If we're making metal, Cu, you need 2 electrons. So that's how I'll get that 1 mole of Cu to 2 mole of electrons. Okay? Now, Faraday's constant relates 1 mole of electron to 96487 coulombs. And so multiplying that together, you get 2976 coulombs over the 804 seconds. Okay? So when we do that, our math is 3.7 amperes, and that is our answer. Okay, and we have reached the end of the problem, the practice problems. So thank you all so much for coming out tonight. Everything will be posted on the SSC YouTube channel. If you have any questions, feel free to reach out. And I hope you all have good luck on your exam. Alrighty, yeah, y'all take care.